What we're going to take a look at now is something called centripetal acceleration. Centripetal refers to an object moving in a circular path and refers to actions acting on the object towards the center of the circle. If we look at this ball, it's moving in a circle. If it's a horizontal circle, then we have a bird's eye view of it. At position A, it's traveling at some velocity v1, shown by this vector here. When it reaches position 2, it is traveling with a velocity vector v2, shown here. So v1 looks like that, v2 looks like that. Now the magnitude of each of those vectors is the same thing. What's changing is the direction. So we have an object traveling at constant speed. It has a changing velocity, however, because the direction is changing. So I'm interested in the changing velocity. So I'm going to take my velocity 1, and I'm going to take my velocity 2. And if I subtract them, it's the same as adding the negative of v2 to v1. So it looks like this. So now this shows v2 being subtracted from v1. So my red vector here is my change in velocity. So now if I move this and I bring it up to the circle and I position it so that my change in velocity is essentially the midpoint between point A and point B, what I see is my change in velocity vector is pointed directly towards the center of the circle. We remember from kinematics that acceleration is defined as the change in velocity over time. Now I have a change in velocity vector up there pointing towards the center of the circle, and it turns out that centripetal acceleration is this acceleration of a constantly speeding object in a circle. Centripetal acceleration points towards the center of the circle and exists even though an object is traveling at a constant speed because the direction of its speed is changing, meaning its velocity changes. In order to make centripetal acceleration a little bit more usable equation, we're going to look at a case of some similar triangles. So first of all, we'll look at our velocity triangle. v1 and v2 are numerically equivalent, and delta v is the difference between them. So we can say that the change in velocity over v, either v1 or v2, is equal to, because we have similar triangles, now we're going to look at a measurement, a length triangle. So point A is where v1 starts. Point B is where v2 starts, and both points can be connected to the center of the circle, and we have a radius. From point A to point B, if it's a very short distance, is equivalent to the chord delta x. So we can say delta x over r is equal to delta v over v1 or v2. We also know that the change in position is equal to our speed, or the absolute value of our velocity, times time. So if we put that in, we have velocity times time over radius equals change in velocity over v. If we reorganize this so that it looks more like our centripetal acceleration equation, we want the t in the denominator. So we have change in velocity over change in time. And to do that, we're going to move the velocity in the denominator over to the right side and put it in the numerator. We end up with v squared over radius. So a more useful way to write centripetal acceleration is with this equation. Centripetal acceleration equals linear velocity squared over the radius. And so there's another equation that we will be working with. Now if I combine that with the definition of velocity, then I can get it in terms of angular velocity as well. So I'm going to take my new centripetal acceleration equation, and I use this equation. So in place of v, I'm going to put omega times r. So my centripetal acceleration, in fact, equals my angular velocity squared times the radius. All right, let's look at a problem here with a golfer having a maximum angular speed. We have 6.3 radians per second. We have two drivers she can choose, one that has a club head 1.9 meters from the axis of rotation, which is probably her hands. The other one's 1.7 meters from the axis, again her hands. We want to find out the tangential or linear speed for the club head of each driver. So velocity in this case is going to be my tangential speed, 6.3 radians per second, times the radius. So for the first club it's 1.9 meters. So the velocity of the club head is 12 meters per second for the first one. We'll do the same thing for the second one. So we have the longer club having a velocity at the head of 12 meters per second. We have the shorter one being 10.7 meters per second. If we look at B, which driver is going to allow the golfer to hit the ball farther and why? Well, hopefully it would make sense that the longer club having a larger velocity is going to be able to transmit the momentum it has to the ball and give the ball a larger velocity, which would then allow the ball to go farther. So now we're bringing in momentum and taking advantage of what we know about that to find out a projectile distance. Finding the centripetal acceleration of each driver, well, we find the linear velocity, so we can take advantage of that, and knowing the radius, we can find each centripetal acceleration. So for the longer club, we have 12 meters per second. We square that, divide by the radius of 1.9 meters. For the shorter club, we have a velocity of 10.7 meters per second and a radius of 1.7 meters. Our centripetal acceleration in this case is 67.3 meters per second squared. All right, our third question, we have a cylindrical space station. It has a radius and it is rotating around an axis with an angular speed, 0.292 radians per second, and we're supposed to figure out the centripetal acceleration at 3 different places. So we'll start out by going at the center of the station. So our centripetal acceleration, we have an angular speed this time, but we have an equation that allows us to relate angular speed with centripetal acceleration. And it is the angular speed squared, so 0.292 radians per second times the radius. Well, at the center of the station, the radius is 0. So our centripetal acceleration is 0 at the center of the station. Halfway out, same angular speed, and half of 115 is 57.5 meters. So we have a centripetal acceleration of 4.9 meters per second squared. Now if I'm at the rim of the space station, same process again, and this time I get 9.81 meters per second squared. So the way that artificial gravity is created in large space stations is to rotate them, and essentially the outer perimeter, the outer circumference of the space station becomes the floor, and you can create an acceleration equivalent to the acceleration due to gravity, so it feels like you have gravity present.